Somewhere in the galaxy, right now, a signal could be crossing empty space toward a world that will not exist by the time it arrives. In 1950, a scientist named Enrico Fermi asked one simple question over lunch. Where is everybody? The math said the galaxy should be full of life. The sky stayed silent. For 70 years, people have blamed distance. They have blamed danger. They have blamed hiding. But the real answer might be hiding in something else entirely. Time. We are going to walk through habitable zones that shift for billions of years, stars that will burn for trillions more, and a black hole where time itself slows to a crawl. Prepare yourselves. If you want more of these deep dives into the universe's biggest mysteries, hit subscribe before we go, because it helps this channel keep making them. We begin. Lunch at Los Alamos, 1950. A group of scientists sat around a table, joking about flying saucers in the newspaper. Then one of them, Enrico Fermi, went quiet. He grabbed a napkin and started doing math. The galaxy holds hundreds of billions of stars. Many of those stars are older than our sun by billions of years. Give any civilization even a small head start, a few thousand years of rockets and radio, and it could spread across the whole galaxy long before we ever showed up. So Fermi looked at his friends and asked four words that still haunt scientists today. Where is everybody? It sounds like a simple question. It is not. Every year, telescopes find more planets that could hold life. Thousands of them now, scattered across the sky like sand on a beach. Statistically, the galaxy should be loud. Instead, when we point our best instruments at the stars, we get static, empty, endless, static. For decades, people have tried to explain the silence. Maybe aliens are too far away to reach us. Maybe they are hiding on purpose. Maybe we are simply alone, a cosmic accident that never repeated. Each idea has fans. Each idea has holes. There is another answer, one that gets less attention, but might matter more than all the others combined. It has nothing to do with distance in space. It has everything to do with distance in time. Think about a play performed in an empty theater. The actors show up one night, perform a brilliant show, and leave. A different group shows up the next night, never knowing the first group existed. The galaxy might work the same way. Civilizations could be rising and falling all the time, just never at the same moment. Fermi's napkin math assumed something simple. It assumed that if civilizations exist, they exist now, ready to be found. But the universe is nearly 14 billion years old. Human civilization has existed for a blink of that. If another civilization rose and fell 1 million years before humans built the first city, we would have no way of knowing. Their signals would have already passed by. Their ruins would have already turned to dust. This changes the entire shape of the paradox. It is not just about whether life exists somewhere out there. It is about whether that life exists at the same slice of time as us, in a universe old enough to hide 1,000 missed connections. The math that once seemed to promise a crowded galaxy starts to look different when you stretch it across billions of years instead of just space. Fermi's napkin is long gone. His question is not. And once you start pulling on the thread of time instead of distance, the paradox does not get simpler, it gets stranger and far more unsettling than anyone expected. Modern astronomers still run versions of Fermi's back-of-the-napkin logic today, just with better numbers. They plug in the number of stars, the fraction likely to have planets, the fraction of those planets that could support life, and the odds that life develops into something intelligent. Almost every version of that math points to the same conclusion. The galaxy should not be this quiet, yet it is. That gap between the math and the silence has a name. Scientists call it the Great Silence, and it remains one of the most debated open questions in modern astronomy. Some blame it on distance, some blame it on danger. Few, until recently, have taken the timing problem seriously enough. Picture the entire history of the universe, stretched out as a single calendar year. The Big Bang happens at midnight on January 1st. Our sun does not even form until late August. Earth cools into a rocky ball a few days after that. Dinosaurs do not show up until the day after Christmas. Humans, all of recorded history, every pyramid and empire and rocket launch happen in the last few seconds before midnight on December 31st. That is how young we are compared to everything else. Now stretch that same calendar back out to real time. The universe is roughly 13.8 billion years old. Our Sun and Earth are only about 4.6 billion years old, meaning the universe was already well over half finished with its history before our solar system even existed. Billions of stars had already been born, lived out their lives, and died before the sun ever lit up. This matters more than it sounds. If planets have been forming around those older stars for billions of years, then civilizations, if they exist, did not have to wait for us to catch up. Some of them could have had a 10 million year head start. Some could have had a billion-year head start. In cosmic terms, a billion years is enormous. It is roughly the same gap between the first single-celled organisms on Earth and the first fish. Here is the problem. A head start that large does not just mean an older civilization. It likely means a civilization that already lived, spread, and vanished long before Earth even had an ocean. Civilizations, if they follow anything like Earth's own history, may not last forever either. Wars end them, disasters end them, or technology simply outpaces wisdom and something goes wrong. If a civilization rises and falls in a few 100,000 years, that is a flash compared to the age of the galaxy. Now imagine millions of these flashes scattered across 13 billion years of cosmic history. The odds of two flashes landing at the exact same moment, close enough to notice each other, start to look less like a guarantee and more like a lottery ticket. This is the piece most conversations about aliens skip over. People imagine the galaxy as a single snapshot, every star and planet existing at once, ready to be explored. But the galaxy is not a snapshot. It is a movie, running for billions of years, with scenes that rarely overlap. Somewhere out there, a species could have built cities and gone extinct before the first single-celled organism on Earth ever divided in two. That thought should make the silence feel less mysterious and more expected, but it also opens a darker possibility. If civilizations really do come and go like brief flashes of light in an old, dark room, then finding one at the same moment as us would not just be rare. It would be a genuine miracle, and miracles are exactly the kind of thing you cannot count on. Some researchers have tried to put real numbers on this idea, building simulations that scatter thousands of pretend civilizations across a pretend galaxy, each one appearing at a random point in time and lasting for some limited stretch before disappearing. The results are almost always the same. Even in a galaxy packed with life, most of those simulated civilizations never overlap with each other at all. They rise, they live out their stretch of time, and they vanish, often without ever sharing the galaxy with a single other mind. Every conversation about the Fermi paradox starts the same way. People ask how far away another civilization might be. 4 light-years to the nearest star, 26,000 light-years to the center of the galaxy, 100,000 light-years across the entire Milky Way. These numbers get thrown around like they explain everything, like distance alone is the reason we have never heard from anyone. But distance is only half the problem, and maybe the smaller half. The real question is not how far away another civilization might be. It is whether that civilization even exists at the same moment we do. Think about 2 people trying to meet at a coffee shop, except neither of them knows the date or the time. One shows up on a Tuesday in March, the other shows up on a Thursday in October, 5 years later. It does not matter that the coffee shop is right across the street from both of their homes. It does not matter how close they live to each other. If their visits never line up, they will never meet, no matter how many times they each show up alone. That is the galaxy. Billions of stars, spread across a disk 100,000 light-years wide, each one running its own private clock. Some stars burned out and died before Earth's oceans even formed. Other stars are just now cooling down enough for planets to form around them at all. Somewhere in that mess of mismatched clocks Life might be starting on 100 different worlds this very second, each one billions of years away from ever building a radio telescope. Distance can be crossed, eventually, with enough time and enough technology. Time cannot be crossed the same way. You cannot send a signal into the past to reach a civilization that already went extinct. You cannot speed up your own evolution to catch up with a civilization that will not exist for another 10 million years. Space is a problem you can chip away at. Time is a wall. This is why the paradox gets darker the closer you look. It is not enough for life to exist somewhere in the galaxy. It has to exist somewhere in the galaxy right now, in a window narrow enough to matter, on a timeline that happens to overlap with ours. Given that the galaxy is 13 billion years old, and human civilization has existed for a few thousand years, that window looks less like an open door and more like a crack in a wall, one that opens and closes fast. Scientists have started calling this idea the temporal Fermi paradox, separating it from the older, more familiar version about distance. It reframes everything. It is not really a search for aliens across space. It is a search for aliens across time, and finding someone who is not just far away, but also awake at the exact same moment we are. That distinction changes every answer that comes next, starting with the very thing that carries any signal we might ever receive. Once you accept that timing matters as much as location, the entire search for life starts to feel different. It stops being a simple question of pointing telescopes in the right direction. It becomes a question of catching a narrow window, one that might open for only a few thousand years out of a 13 billion year history, and hoping that window happens to line up with our own. Look up at the night sky, and you are not seeing the universe as it is right now. You are seeing the past, layered on top of more past, stacked into a single glowing picture. Light does not travel instantly. It moves at about 186,000 miles every second, which sounds impossibly fast until you try to cross the distances between stars. The nearest star to our Sun, Proxima Centauri, sits about 4 light-years away. That means the light hitting your eyes tonight left that star 4 years ago. You are looking at a 4-year-old postcard. Now zoom out further. The center of our galaxy is about 26,000 light-years away. Any light or signal from there left before the pyramids were built, before written language existed, before humans had even settled into permanent villages. It has been traveling this entire time, carrying news from a moment in history so old that entire civilizations on Earth were born and buried while it crossed the dark. This is the trap hiding inside every search for alien signals. If a distant civilization sent a radio broadcast toward Earth 20,000 years ago, we might only be picking it up now. And if they are still alive today, they have had 20,000 more years to change, evolve, or vanish completely since that signal left home. Every message from space is a letter, but the sender might not exist anymore by the time we finish reading it. Flip the problem around, and it gets even stranger. If humans sent a signal out into the galaxy today, using our fastest radio technology, it would take tens of thousands of years just to reach the center of the Milky Way. By the time any alien civilization received it, human history as we know it could be unrecognizable. Cities could be gone, languages could be forgotten. The people who sent the signal would be nothing but old bones and older stories. So when scientists point telescopes at the sky searching for a signal, they are not really searching for aliens who exist right now. They are searching for evidence that aliens existed at some point in the past, wrapped inside a beam of light old enough to have crossed unimaginable distances. Finding that signal would not prove anyone is out there today. It would only prove that someone, somewhere, existed long enough ago to leave a mark. This is why the search for alien life is really 2 searches stacked on top of each other. First, did anyone ever exist to send a message? Second, did that message happen to be aimed our direction, at exactly the right angle, launched at exactly the right time in the deep past, to arrive during the narrow slice of history when humans built telescopes capable of catching it? Every star twinkling above you tonight might be broadcasting secrets from thousands of years ago, secrets about civilizations that could have already come and gone before we even knew to listen. Even our closest cosmic neighbors carry this same delay. When astronomers study a galaxy millions of light years away, they are not looking at that galaxy today. They are looking at light that left millions of years before humans existed at all. Every telescope pointed at the sky is, in a very real sense, a time machine, one that only looks backward and can never show us the present moment happening anywhere else in the universe. Somewhere in the galaxy, 1,000,000 years ago, a civilization might have looked up at its own night sky and asked the exact same question we are asking right now. Are we alone? They might have built cities, launched satellites, even sent signals into the dark hoping someone, someday, would hear them. And then, for reasons we will never know, they stopped. 1,000,000 years sounds like an unimaginable stretch of time, and for a single human life, it is. But for the galaxy, it is barely a passing moment. Stars live for billions of years. The galaxy itself has existed for over 10 billion years. Against that backdrop, 1,000,000 years is a single page in a book with 1,000,000,000 pages. Here is what makes this idea so unsettling. If a civilization rose and fell 1,000,000 years before humans existed, there would be almost nothing left to find. Their cities, if built from anything like our materials, would have crumbled into dust long ago. Wind, water, and time erase almost everything given enough centuries. Even something as massive as a skyscraper would not survive 1,000,000 years of erosion. Their satellites would have fallen out of orbit. Their radio signals would have already swept past Earth and kept traveling, thinning out into the background noise of space, indistinguishable from static. We know this because we can look at our own planet. Evidence of human civilization 10,000 years ago is already hard to find. Entire cities from just a few thousand years back have been buried under sand and jungle, discovered only by accident. Now stretch that same erosion out across 1,000,000 years, and almost everything a civilization ever built would be gone, not destroyed by war, not wiped out by disaster, simply worn away by time itself, the same slow force that turns mountains into hills. This means the absence of evidence is not necessarily evidence of absence. Scientists have a phrase for this exact trap. It does not mean nobody was ever there. It might only mean we arrived too late to see the wreckage. Think about walking into a house where a party clearly happened. The lights are off, the trash has been cleaned up, the guests are long gone. You missed it, but that does not mean the party never happened. It means you showed up after everyone else already left. The galaxy might be full of these missed parties, civilizations that came, built something remarkable, and packed up long before humans ever climbed down from the trees. If this is true, the silence we hear from space is not proof that we are the first or the only ones. It may simply be the sound of an empty room after everyone else has already gone home. A room we walked into thousands or millions of years too late to catch anyone still standing there. Even our own achievements would fade this way. If humanity vanished tomorrow, most cities would be unrecognizable within 20,000 years, swallowed by forests, deserts, or rising seas. Give it 1,000,000 years, and almost nothing man-made would remain at all. The only lasting trace might be a thin, strange layer buried in the rock, waiting for some future visitor to stumble across it by accident. Stars are not born all at once. The galaxy did not flip a switch 13 billion years ago and light up every star at the same instant. Stars are still forming today, right now, inside massive clouds of gas and dust scattered across the Milky Way. Other stars, meanwhile, burned out and died long before Earth's oceans ever existed. The galaxy is less like a single event and more like a city where new buildings go up and old ones get demolished, over and over, for billions of years straight. This staggered timeline matters enormously when it comes to life. A star needs time to settle down before its planets can become stable enough to support anything alive. Then, those planets need time to cool, form oceans, and build the right chemistry. Then, if Earth is any guide, Life needs billions of years just to crawl from simple cells to something as complex as a fish, let alone a species that builds telescopes. On Earth, this entire process took about 4.5 billion years. Simple, single-celled life showed up relatively fast, within the first billion years or so. But complex life, the kind with organs and brains, took nearly 3 billion more years to arrive. If that timeline holds true across the galaxy, then any planet hoping to develop intelligent life needs a star that has been shining steadily for at least 4 billion years without any interruptions. Not every star gets that chance. Massive stars, the kind many times bigger than our Sun, burn through their fuel in just a few million years before exploding. A few million years is nowhere near enough time for complex life to develop, even if the conditions were otherwise perfect. These giant stars live fast and die young, more like a firework than a furnace. And any planets orbiting them never get the billions of years needed to grow something as complicated as a brain. Smaller, longer-lived stars like our Sun offer a better shot, but even they only last around 10 billion years before running out of fuel. That gives evolution a window, but not an endless one. If intelligent life needs 4 billion years to develop, and a Sun-like star only lasts about 10 billion years total, that leaves a narrow band of time in the middle where a civilization could actually rise and still have a stable star left to live under. Now multiply this timing puzzle across hundreds of billions of stars, each one born at a different moment, each one offering a different-sized window for life to develop. Some windows never open at all, some open and close before anything complex can crawl through. The galaxy is not one clock ticking for everyone. It is billions of separate clocks, each one running on its own schedule, rarely lining up with any of the others. Picture a row of hourglasses. Each one started at a different moment, each one holding a different amount of sand. Some run out before anything interesting happens on the planet spinning beside them. Others still have plenty of sand left, but the planet orbiting that star has not yet reached the stage where anything complex could exist. Only a rare few hourglasses ever line up so that enough sand remains at exactly the moment intelligent life is ready to appear. And even among the stars that do offer enough time, there is one more filter working against life before it even gets a chance to begin. Not every part of the galaxy is a fair shot at life. Picture the Milky Way from above, a giant spinning disk of stars shaped almost like a flattened pinwheel. Scientists believe there is a specific ring inside that disk, a narrow band called the galactic habitable zone, where conditions are calm enough and rich enough in the right materials for life to have any real chance at all. Get too close to the center of the galaxy and things turn violent fast. The core of the Milky Way is packed with stars crowded closely together, along with a supermassive black hole millions of times the mass of our Sun. That crowding means far more stellar explosions, far more radiation, and far more gravitational chaos than any planet needs while trying to keep life alive. A planet near the galactic center is like a house built in the middle of a demolition site. Even if it survives one disaster, another one is never far behind. Move too far to the outer edges of the galaxy, and a different problem shows up. Out there, stars are spread thin, and the raw materials needed to build rocky planets, elements like iron, carbon, and oxygen, become scarce. Those heavier elements are forged inside dying stars and scattered through explosions called supernovae. The outer galaxy simply has not had enough of those explosions yet to build up rich planetary ingredients. It is like trying to bake a cake in a kitchen that is still waiting for half its ingredients to arrive. Somewhere between those two extremes sits the habitable zone, a ring roughly 19,000 to 31,000 light-years from the galactic center. Our own solar system sits comfortably inside that ring, about 26,000 light-years out, far enough from the chaos at the core, close enough to have the heavy elements needed to build a rocky world like Earth. This changes the entire scale of the search for life. Out of the roughly 200 billion stars in the Milky Way, only a fraction sit inside this ring at all. And of those, only a fraction will have stars that live long enough, in the way we covered before, to give life the billions of years it needs to grow complex. The pool of candidates shrinks fast, star by star, filter by filter, the way a single football field of applicants can shrink down to a handful after enough rounds of cuts. And even inside that ring, the danger is not over. Being in the right neighborhood does not mean the neighborhood stays safe forever. Stars move, galaxies shift, and every few 100 million years, something far more violent than a black hole can sweep through an otherwise perfect stretch of space, wiping out everything in its path without warning. Astronomers describe this ring the same way a city planner might describe a safe zone on a map, an area protected from flooding on one side and wildfire on the other. But maps change. A safe zone today is not guaranteed to stay safe for the next billion years. The galaxy keeps spinning, stars keep drifting, and the ring itself slowly shifts outward over time as heavier elements spread further from the core. Nothing about this safe zone was built to last forever. Somewhere out in the galaxy, a massive star is dying. When stars, many times bigger than our sun, run out of fuel, they do not fade quietly. They collapse in on themselves and explode in one of the most violent events the universe can produce, called a gamma-ray burst. For a few seconds, that explosion can outshine an entire galaxy. And if a planet happens to be lined up in the direct path of that beam, the consequences are catastrophic. A gamma-ray burst does not need to be close to cause damage. Even from thousands of light years away, a direct hit could strip away a planet's ozone layer, the thin shield that protects life from deadly ultraviolet radiation. Without that shield, radiation from the planet's own star could pour down onto the surface, damaging DNA on a massive scale and collapsing entire food chains within months. Some scientists believe an event like this may have already happened to Earth, contributing to one of the largest mass extinctions in our planet's history hundreds of millions of years ago. Here is the part that connects back to the bigger mystery. Gamma-ray bursts are not gentle or forgiving. They are more like a reset button, one that can wipe out complex life across a wide stretch of the galaxy in a matter of seconds, without any warning at all. A civilization could spend 4 billion years slowly climbing from simple cells to cities and telescopes, only to be erased by a burst of radiation from a dying star it never even knew existed. This is sometimes called neocatastrophism, the idea that events like gamma-ray bursts act as a kind of galactic janitor, sweeping through regions of space and clearing out complex life before it has a chance to become something like us. Early in the galaxy's history, when heavier, more explosive stars were more common, these resets may have happened often, hitting large sections of the galaxy again and again before life ever had a real shot at sticking around. Think about trying to build a sandcastle on a beach where a massive wave rolls in every few 100 million years, flattening everything in its path without warning. No matter how carefully the castle gets built, no matter how much time and effort goes into it, the ocean does not care. It simply resets the beach and starts over. If gamma-ray bursts have been quietly erasing pockets of complex life across the galaxy for billions of years, then countless civilizations may never have made it far enough to send a single signal, let alone build a spacecraft. The silence we hear from space might not mean life never started. It might mean life kept getting knocked back down to zero, over and over, before it ever had the chance to stand up and speak. And even where the beam missed, an even slower, quieter force has been working against every civilization the entire time. There is a strange kind of comfort hidden in this idea, even with how brutal it sounds. It means the silence from space is not necessarily a story about failure or extinction by war. It could simply be a story about bad luck, about a beam of radiation crossing paths with a planet at exactly the wrong moment in its 4 billion year climb toward complexity, ending the story before it had any chance to be told. If you want to understand how rare intelligent life might be, you do not have to look at distant stars at all. You can look at Earth's own history, because our planet already shows exactly how narrow the window for intelligence can be, even when everything else goes right. Earth formed about 4.5 billion years ago. Simple life, just basic single-celled organisms, appeared surprisingly fast after that. within the first several 100 million years. That sounds encouraging. Like life is eager to start the moment conditions allow it. But then something strange happened. Life stayed simple. For nearly 3 billion years, Earth was covered in nothing but basic microscopic organisms. No plants, no animals, no brains of any kind. Just endless generations of simple cells floating in oceans, doing very little that looked like progress. It was not until roughly 600 million years ago that complex, multicellular life finally exploded onto the scene during a period scientists call the Cambrian explosion. Suddenly, in a relatively short span of time, oceans filled with strange new creatures, the earliest ancestors of nearly every animal alive today. From there, evolution kept building. Fish became amphibians. Amphibians became reptiles. Eventually, after hundreds of millions of more years, some of those creatures became mammals, then primates, then something that could ask questions about its own existence. Modern humans, the kind capable of language, art, and eventually science, have only existed for around 300,000 years. Civilization, meaning cities, writing, and organized technology, is barely 10,000 years old. Out of 4.5 billion years of Earth's history, intelligent civilization has existed for a sliver so thin it barely registers on the timeline at all. This matters because it shows just how many steps had to happen, one after another, before anything like a human ever stood up and looked at the stars. Simple life was fast. Complex life took nearly 3 billion years longer. Intelligence took even longer than that. If any one of those steps had taken slightly longer, or never happened at all, there would be no humans here to ask why the universe is silent. Now stretch that same uncertainty across every other planet in the galaxy. Even if a planet has the right star, the right elements, and enough time, there is no guarantee it follows the same path Earth did. Life might get stuck at the simple stage forever. Complexity might never emerge. Intelligence might stall out entirely, the same way it seemingly did on Earth for billions of years before finally breaking through. Earth's own story suggests that reaching intelligence is not a guaranteed outcome of time. It might be closer to a lucky roll of the dice, repeated successfully again and again, against odds that could easily have gone the other way. Some scientists call this the Gaian bottleneck, the idea that most planets with life get stuck early, never developing the stable feedback loops needed to keep a planet livable long enough for anything complex to emerge. If that idea holds true, then countless worlds across the galaxy might already be full of simple, single-celled life right now, quietly existing in oceans that will never produce anything more advanced than what Earth had 3 billion years ago. Earth's timeline just proved something uncomfortable. Complex life took nearly 4 billion years to develop from the very first spark of biology. That number is not a small detail. It is a requirement. Any planet hoping to follow the same path needs a star that stays stable and steady for at least that long without any major interruptions. Here is the problem. Most stars in the galaxy do not last that long at all. Massive stars, the bright, blazing giants, many times larger than our sun, burn through their fuel at a reckless pace. Some of the largest stars in the galaxy live for only a few million years before collapsing and exploding as supernovae. A few million years might sound like plenty of time from a human perspective, but compared to the 4 billion years Earth needed just to develop complex life, it is barely a passing moment. It would be like trying to bake a cake in an oven that shuts off after 10 seconds. Even mid-sized stars, ones closer in size to our own sun, only last around 10 billion years total before running out of hydrogen fuel. That gives evolution a real window, but not an unlimited one. If a planet needs 4 billion years just to reach the complexity of a jellyfish, and its star only burns steadily for 10 billion years total, that leaves a narrow stretch in the middle where intelligent life would need to appear before the star starts to change and threaten the planet's habitability. This means the galaxy is filled with an enormous number of stars, that were simply never in the running for producing intelligent life at all. The massive, fast-burning giants disqualify themselves almost immediately, exploding long before biology could even get past its earliest stages. Only the more modest, longer-lived stars offer any real shot, and even among those, the timing has to work out almost perfectly. Think of it like a relay race with an incredibly tight time limit. Every stage of life, from simple cells to complex organisms to actual intelligence, has to be completed one after another, all within the lifespan of a single star. Miss the deadline, even by a little, and the star begins to change in ways that make the planet uninhabitable before the race is finished. As a sun-like star ages, it grows brighter and hotter, slowly cooking any planet that once sat comfortably in its habitable zone. Oceans boil away, atmospheres thin out. A world that looked perfect for billions of years can turn hostile in a relatively short stretch near the end. This single filter alone eliminates a staggering number of potential homes for intelligent life throughout the galaxy. Every blazing, short-lived giant star in the sky, the kind that lights up entire nebulae and dominates the night with its brightness, is quietly disqualified from ever hosting a civilization, no matter how many planets orbit it or how perfect those planets might otherwise be. But there is one category of star that breaks this entire rule, one that does not burn out in millions or even billions of years, but instead keeps shining for a length of time so enormous it barely makes sense to the human mind. Most stars in the galaxy are not giants. They are small, dim, and easy to overlook, called red dwarfs. They make up roughly 80% of every star in the Milky Way, which means the vast majority of stars around us are nothing like our own sun at all. They are smaller, cooler, and far less flashy. But what red dwarfs lack in brightness, they make up for with something far more valuable to the story of life: time. Where a star like our sun burns through its fuel in about 10 billion years, red dwarf stars sip their fuel at an incredibly slow pace. Scientists estimate that red dwarfs can burn steadily for 1 trillion to 10 trillion years before finally running out of hydrogen. To put that number into perspective, the entire universe so far has only existed for about 13.8 billion years. A single red dwarf star could keep shining for a length of time roughly 100 times longer than the current age of the universe itself. This changes everything about the timing problem covered earlier. If complex life needs about 4 billion years to develop, and a star like our sun only offers a window of around 10 billion years total, that leaves a tight, narrow stretch of time for intelligence to appear. But a red dwarf, burning steadily for trillions of years, offers an almost unimaginable amount of extra time. 4 billion years, the length it took Earth to build a jellyfish, a fish, a mammal, and eventually a human, becomes a tiny fraction of a red dwarf's total lifespan. Instead of nearly the entire clock, there are real challenges to overcome first. Planets orbiting red dwarfs typically have to sit much closer to their star to stay warm enough for liquid water, since red dwarfs put out far less heat and light than our sun. Sitting that close brings other dangers, like intense flares and radiation blasting the planet's surface. Scientists are still studying whether life could survive under those harsher conditions. But if it can, and if it manages to hold on, that planet would have more time to develop complexity than almost any planet orbiting a star like our sun ever could. This detail becomes one of the most important pieces of the entire puzzle. If red dwarf stars, the most common type of star in the galaxy, can eventually support life given enough time, then the universe is not running out of chances anytime soon. It has barely started handing them out. Scientists like Harvard astronomer Avi Loeb have pointed out that the coolest, smallest red dwarfs, the ones that will burn the longest, are only just now old enough for their planets to have had a real shot at complex life. Most of them are still far too young. Their planets have barely had time to settle, let alone climb the long ladder from simple cells to something that builds telescopes. Because here is the part that changes the whole conversation. If stars can keep burning for trillions of years, and the universe itself is only 13.8 billion years old so far, then something extraordinary becomes true about exactly where we stand in the story of the cosmos. Here is a number that should stop you in your tracks. If red dwarf stars can burn for up to 10 trillion years, and the universe has only existed for 13.8 billion years so far, then less than 1% of the universe's potential lifespan for star-powered life has even happened yet. Less than 1%. We are not living in the middle chapters of a long cosmic story. We are living somewhere near the very first page. This idea flips the entire Fermi paradox on its head. For decades, the silence from space has been treated as a mystery, something that needs an explanation because the universe should already be full of advanced civilizations by now. But that assumption only holds up if the universe has already had enough time for life to fully play out everywhere it possibly could. If red dwarf stars are correct, and most stars in the galaxy have trillions of years left to burn, then the universe has not run out of time for life. It has barely begun handing out the opportunity at all. Think about showing up to a massive stadium hours before any event begins. The seats are mostly empty. The lights are still being tested. It would be easy to assume nobody is coming, that the whole event has been cancelled. But the truth might simply be that you arrived incredibly early, long before the stadium was ever expected to fill up. That same logic applies to the galaxy. If most stars capable of supporting life are red dwarfs, and those stars are just now reaching the ages needed for their planets to develop stable, long-term conditions, then civilizations capable of communication may not have had nearly enough time to appear yet, let alone spread across the galaxy. The stadium is not empty because nobody is coming. It might be empty because the show has not started. This reframes the entire search for alien life. Instead of asking why the galaxy looks empty despite having had plenty of time, the better question becomes whether the galaxy has had anywhere near enough time at all. 13.8 billion years feels enormous to a species that has only existed for a few 100,000 years. But compared to the 10 trillion year lifespan of a single red dwarf star, 13.8 billion years is barely a rounding error. If this idea holds up, it means something remarkable about humanity's place in the story of the universe. We may not be late arrivals to a galaxy that has already been explored, mapped, and settled by older civilizations. We may be among the very first, standing in an empty stadium hours before anyone else even shows up to take their seats. This is a strange thing to sit with. Every generation of humans has assumed the universe was already finished, already explored, already claimed by someone else. The idea that we might instead be standing near the opening act of an unimaginably long show reframes not just the silence in space, but humanity's entire sense of its own timing. And if that is true, one particular idea becomes worth taking seriously, an idea that some scientists have started calling the most hopeful explanation for the silence yet discovered. Astronomers have a term for the current era of the universe. They call it the stelliferous period, the long stretch of cosmic history when stars are actively forming, burning, and providing enough light and heat for planets to potentially host life. This period began a few 100 million years after the Big Bang, once the first stars ignited, and it is expected to continue for trillions of years into the future, as long-lived stars like red dwarfs keep shining. Right now, 13.8 billion years into the universe's history, we are sitting near the very beginning of that stelliferous period, not the middle, and nowhere close to the end. Trillions of years of star formation and star-powered energy remain ahead. Entire future eras of the universe, ones filled with far more stars and far more opportunities for planets to form, have not even happened yet. If the universe eventually runs out of new stars entirely, some scientists estimate that will not happen for another 100 trillion years or more. This puts humanity's current moment into a strange kind of perspective. We often imagine advanced civilizations as something ancient, species that have existed for millions or billions of years, far more evolved than us. But if the stelliferous period has trillions of years left to run, and most of the universe's usable stars have not even reached their most stable, life-friendly ages yet. Then very few civilizations, if any, have had the chance to become truly ancient at all. Everyone, potentially including us, could be equally early. Picture a brand new city being built from scratch. In the first few years, only a handful of buildings go up. Streets are half finished. Most of the land sits empty, waiting to be developed. It would be a mistake to assume that empty land means the city failed, or that nobody wants to live there. It might simply mean construction just started, and the busiest, most crowded version of that city will not exist for decades to come. The galaxy might be that half-built city. Most of its usable stars, the red dwarfs capable of burning for trillions of years, have barely had enough time to reach the point where their planets could support anything as complex as intelligent life. The busiest, most crowded era of the galaxy, one potentially filled with countless civilizations, might not arrive for hundreds of billions or even trillions of years from now. If that is true, it does not mean the universe is empty forever. It means we might be looking at the opening pages of an extraordinarily long book, one that has barely begun, with almost the entire story still left to be written by whoever comes next, possibly even by us. Some astronomers describe this future era using a strange phrase, calling it the true habitable epoch of the universe, a period potentially trillions of years from now, when far more stars will have reached the right age, and far more planets will have had the time needed to grow something intelligent. Compared to that distant future, right now might be remembered, if anyone is ever around to remember it, as the very first flicker of light in an otherwise dark and empty room. For most of human history, people have assumed the opposite of what the evidence now suggests. The common belief has always been that if intelligent life exists anywhere else, it almost certainly got there first. Older, wiser, more advanced, civilizations that have had millions of extra years to build technology far beyond anything humans can imagine. Under that assumption, humanity looks like the exception, a late arrival stumbling onto a galaxy that older species have already mapped out. But the timeline covered so far tells a very different story. If most of the galaxy's longest-lived stars are red dwarfs capable of burning for trillions of years, and the universe itself is still in the earliest fraction of its total lifespan for supporting life, then very few civilizations anywhere could have had the kind of enormous head start people usually imagine. Being ancient requires time, and there simply has not been very much of it yet, cosmically speaking. This flips the entire assumption on its head. Instead of being late to a party that has been going on for billions of years, humanity might be one of the first guests to arrive at a party that has barely started setting up. Scientists have started calling this the "we are early" hypothesis, and it treats humanity not as an unusual exception to the rule, but as an early example of something that could eventually become common throughout the galaxy. Think about being one of the very first people to move into a brand new neighborhood while it is still under construction. There are no crowded streets yet, no established shops, no decades of history built up around you. It is not because something is wrong with the neighborhood, it is because you showed up before almost everyone else. Being early does not mean being unwanted, it simply means being first. If this hypothesis holds up, it changes how we should think about the silence coming from space. It is not that other civilizations are hiding from us, or that something destroyed them before we could find them. It might simply be that intelligent life needs an enormous amount of time to develop, and even after 13.8 billion years, the universe has barely handed out enough of that time for very many species to get there yet. This does not mean humanity is guaranteed to succeed, or that the galaxy will eventually fill up with civilizations no matter what happens. It only means the timing lines up in a way that makes early arrival a real possibility, rather than a strange coincidence that needs some other explanation. And if humanity really is early, rather than late, that single idea reshapes the entire meaning behind the silence we have been hearing from the stars all along. There is something almost dizzying about standing at the front of a story this large. every civilization that could ever exist after us will look back at this exact moment, 13.8 billion years into the universe's history, as the very beginning of everything. If humans manage to survive long enough, we may not be remembered as latecomers who missed the party. We could be remembered as the ones who arrived first and helped set up the room. For decades, the silence coming from space has been treated as bad news. No signals, no structures, no confirmed evidence of anyone else out there. It feels like proof that the galaxy is empty, that humanity really is alone in the dark. But everything covered so far points toward a very different interpretation, one that turns that silence from a tragedy into something closer to timing. If humanity really is early, arriving near the beginning of the stelliferous period instead of somewhere in the middle or near the end, then the silence does not mean nobody is out there. It means almost nobody has had enough time to get there yet. The galaxy is not empty because life failed to happen. It is quiet because most of the stars capable of supporting life over the long haul are still incredibly young, cosmically speaking, and their planets have not had anywhere near enough time to develop anything as complex as a civilization. This is one of the most important distinctions in the entire conversation. Absence of evidence has often been treated as evidence of absence, the idea that if nobody has found aliens yet, it probably means aliens do not exist. But if the timing argument holds up, silence becomes something closer to evidence of an early moment, not evidence of an empty universe. Nobody has shown up to the party yet, not because the party got cancelled, but because the invitations only just went out. Picture a farmer walking through a field the day after planting seeds. Nothing has sprouted yet. No green shoots, no signs of life poking through the dirt. It would be a mistake to assume the seeds failed, or that nothing will ever grow there. The truth is simply that not enough time has passed. Growth takes time, and checking too early will always look like failure, even when everything underground is working exactly as it should. The galaxy might be that field, checked far too early by a species that only just learned how to look. Life may be quietly developing on distant worlds around slow-burning red dwarf stars right now, worlds that will not produce anything resembling intelligence for another billion years or more. From our perspective, that looks like silence. From the universe's perspective, it might just be patience. This does not answer every part of the mystery. Even if the timing argument is correct, it still leaves open one of the strangest problems of all. Even if two civilizations do eventually exist at the same rough moment in cosmic history, actually finding each other across the staggering size of the galaxy brings a whole new set of obstacles, ones that have nothing to do with when life begins, and everything to do with simply reaching across the dark in time to say hello. Astrobiologists who study this question often describe the "we are early" hypothesis as the most hopeful explanation on the table, precisely because it does not require anything to have gone wrong. No wars, no filters, no hidden dangers waiting to erase every civilization before it grows up. It only requires patience, and a universe still young enough to be waiting for the rest of its story to unfold. Even if two civilizations manage to exist at roughly the same point in cosmic history, that alone does not guarantee they will ever find each other. The galaxy is enormous, spanning about 100,000 light-years from edge to edge. Two civilizations could both be alive right now, both curious, both listening to the sky, and still miss each other entirely, simply because of how communication actually works across distances that large. Imagine two people trying to have a conversation by mailing letters across an ocean, except each letter takes centuries to arrive instead of days. One person writes a message and sends it out. By the time it reaches the other side, decades or centuries have passed. If the person receiving that letter writes back immediately, their reply will take another few centuries just to make the return trip. A single exchange, one question and one answer, could easily take longer than either person's entire lifetime to complete. Now, scale that problem up to the size of the galaxy. Radio signals, the fastest form of communication humans currently understand, travel at the speed of light. That sounds instant on Earth, where light can cross the entire planet in a fraction of a second. But across interstellar distances, light suddenly becomes painfully slow. A signal traveling from one side of the galaxy to the other would take roughly 100,000 years just to make the trip one way. This means two civilizations could both exist for thousands of years, both actively broadcasting signals into space, and still never manage to have anything resembling a real conversation. By the time a message from one civilization reaches the other, the sender might have already changed dramatically or vanished completely. And even if the message is received and understood, any reply would take just as long to travel back, potentially reaching a civilization that no longer exists to read it. Scientists studying this problem describe it using the idea of causal contact, meaning two civilizations only really count as connected if they can exchange messages within a time frame that matters to both of them. Existing at the same rough moment in history is not enough. They also need to be close enough and patient enough for an actual back-and-forth conversation to unfold before either side disappears. Computer models built to study this problem often find that most simulated civilizations across a galaxy like ours never actually achieve real causal contact with each other, even when many of them exist during overlapping windows of time. Being alive at the same moment turns out to be only the first requirement. Being close enough to actually talk turns out to be an entirely separate challenge. These same models suggest that when contact does happen, it rarely happens between just two civilizations at a time. Instead, small clusters of worlds close enough to maintain contact tend to form their own separate bubbles, isolated from other clusters on the far side of the galaxy that are having a completely different conversation on a completely different timeline, unaware that the other group even exists. The galaxy might not be one connected community. It might be dozens of small, disconnected ones, each unaware of the others. Suppose humanity decided today to send a single radio message toward the center of the galaxy, aimed at any civilization that might be listening. That signal would leave Earth traveling at the speed of light, the fastest speed anything in the universe can move. It would cross the orbit of Mars within minutes. It would leave our entire solar system behind within about a day, and then it would keep going, alone, into the emptiness between the stars for thousands and thousands of years. The distance from Earth to the center of the Milky Way is roughly 26,000 light-years. That means a message sent today would not arrive at the galactic core until the year 28,000 and something, a span of time longer than all of recorded human history combined, stacked more than twice over. Everything humans have ever built, every language, every empire, every war, and every invention happened within a window shorter than the time it would take that single message to complete its journey. Now, think about who might actually be there to receive it. Human civilization is only about 10,000 years old, counting from the earliest cities and writing systems. Modern industrial society is barely a few centuries old. If a message takes 26,000 years to arrive somewhere, there is no guarantee humanity will even exist in the form it does today by the time that message reaches its destination. Entire nations could rise and fall. Entire species could evolve and change beyond recognition. The message would still be traveling, patient and unaware, carrying words written by people who existed for only a tiny sliver of that entire journey. This cuts both ways. If an alien civilization sent us a message 26,000 years ago, back when humans were living in small hunter-gatherer bands with no writing and no permanent cities, that signal could be arriving on Earth right now, tonight, without anyone realizing it. And the civilization that sent it might have changed so dramatically since then, or vanished entirely, that even a successful reply from Earth would arrive at an empty, silent world on the other end. A single round-trip conversation, one message sent and one reply received, would take about 52,000 years to complete across that same distance. 52,000 years ago, humans had not yet invented farming. Cities did not exist. Written language was not even a concept yet. That is the timescale required for a single exchange of hello and hello back, stretched across a galaxy this large. This is the harsh reality hiding behind every hopeful signal humans send into space. A message is easy to send. Waiting long enough to hear anything back is an entirely different kind of challenge, one that stretches far beyond the lifespan of the civilization that sent it in the first place. Humans have already sent a handful of these messages, tiny plaques and recordings launched aboard spacecraft decades ago, along with a few deliberate radio broadcasts aimed at distant star clusters. Every one of them is still traveling right now, carrying a piece of this exact moment in history toward a future so distant that nobody alive today will ever know if anyone was there to receive it. Imagine a civilization decides to reply to that same message we sent toward the galactic center. They receive it 26,000 years from now, get excited, and immediately fire back a response. That reply then has to travel the same 26,000 light years back to Earth, arriving roughly 52,000 years after the original message left home. By then, the people who sent the first message would be as distant from whoever receives the reply as the earliest cave paintings are from us today. This is the strange math hiding behind any hope of a real conversation across the galaxy. A single round trip, one hello and one hello back, could easily outlast the entire civilization that started it. Empires rise and fall in a few thousand years. Languages change so much in just a few centuries that old texts become unreadable without translation. 52,000 years is not just a long wait. It is long enough for the sender to become mythology by the time any answer finally shows up. Think about writing a letter, sealing it in a bottle, and tossing it into the ocean, knowing it will not wash ashore for 50,000 years. By the time anyone reads it, your language will be forgotten. Your country will not exist. Even the coastline where you tossed it might have shifted into an entirely different shape. Whoever eventually finds that bottle would be reading a message from a version of history so old it barely resembles anything they know, the way a modern reader might struggle to recognize the earliest scratch symbols humans ever carved into stone. This is why scientists studying interstellar communication rarely talk about it the way people talk about a phone call or an email. They describe it more like leaving a monument, something built to be discovered long after the builders are gone, rather than a message meant for an immediate reply. The pyramids of Giza have stood for over 4,000 years, and even they are young compared to the timescales involved in a single galactic conversation. If any civilization out there sent us a message today, the most realistic outcome is not a friendly exchange of information. It is something closer to archaeology. Humans someday digging through a signal the way historians dig through ancient ruins, trying to understand a culture that vanished long before the message even finished crossing the stars. This raises an uncomfortable question. If a genuine back-and-forth conversation between two civilizations requires patience, measured in tens of thousands of years, does communication across the galaxy even count as a conversation at all? Or is it closer to two ships passing in the night, each one leaving behind a message in a bottle that the other will only ever read as ancient history? There is a strange kind of comfort buried inside that discomfort, though. A monument does not need a reply to matter. The pyramids still mean something to the people who visit them today, even though the builders never knew that visitors thousands of years in the future would stand there wondering about their lives. A message sent into the galaxy might work the same way, valuable simply for having existed. Whether or not anyone ever manages to send something back, scientists have a specific term for two civilizations that can realistically exchange messages within a meaningful amount of time. They call it causal contact, and it requires far more than simply existing at the same rough moment in history. It requires two civilizations to be close enough and to last long enough that a message and a reply can both arrive while both sides are still around to care about the answer. Think of causal contact like two people trying to have a conversation while standing at opposite ends of a massive canyon, shouting across the gap. If the canyon is small enough, their voices carry back and forth easily. But if the canyon grows too wide, the sound takes so long to cross that by the time a reply comes back, the person who first called out has already walked away, or grown old, or forgotten the question they originally asked. For two civilizations to achieve real causal contact, they need to satisfy several conditions at once. They both need to exist during an overlapping stretch of time. They need to be close enough that a signal can cross the distance while both sides are still alive to send and receive it. And ideally, both civilizations need to last long enough that an actual exchange of ideas, not just a single ping, becomes possible before either side goes extinct or moves on to something else entirely. This is a much higher bar than most people imagine when they picture contact with an alien species. It is not enough for a civilization to simply exist somewhere in the galaxy. It has to exist in a very specific bubble of space and time, one that intersects with our own bubble closely enough that a meaningful relationship, not just a single one-way broadcast, becomes physically possible. A brief hello shouted into the void does not count as contact if nobody on the other end lives long enough to hear it. Researchers who study this question using computer simulations often find that the number of civilizations able to achieve causal contact with each other is dramatically smaller than the total number of civilizations that might exist across the galaxy's entire history. Most simulated civilizations, even in models where life is fairly common, end up isolated, either because they exist too briefly or because they are simply too far from any other civilization that happens to exist during the same window. This reframes the entire search for alien life one more time. It is not enough to ask whether life exists elsewhere in the galaxy. It is not even enough to ask whether that life exists at the same moment in history as us. The real question becomes whether that life exists close enough and lasts long enough to actually fall within our shared bubble of causal contact, a bubble that might be far smaller than anyone originally assumed. That bubble shrinks even further once you consider how much has to go right at once. A civilization within range might still miss the window if its own lifespan is short, ending before a reply could ever arrive. Even a near neighbor, in cosmic terms, could turn out to be a near miss in every sense that actually matters. Astrophysicist Duncan Forgan decided to test all of this directly instead of just theorizing about it. He built a computer model of the galaxy, using the galactic habitable zone described earlier, and let thousands of pretend civilizations appear at random points within it, each one lasting for a limited stretch of simulated time before disappearing again. The rules of his simulation were simple. Two civilizations could only communicate if they existed during an overlapping window of time and were close enough for a signal to reach between them before either side vanished. Then he ran the simulation over and over, changing the number of civilizations, their average lifespans, and how far apart they tended to appear, watching to see how often real causal contact actually happened. Even small changes to these starting assumptions produced wildly different outcomes, which itself says something important about how sensitive this entire problem is to details. Nobody can currently measure with any real confidence. The results were not encouraging for anyone hoping the galaxy is full of chatting civilizations. Across most versions of the simulation, only a small fraction of the pretend civilizations ever achieved genuine contact with another one. Even when the simulation included a large number of civilizations scattered generously throughout the galaxy, most of them still ended up isolated, either because their lifespans were too short or because the timing simply never lined up closely enough with a neighbor. Picture thousands of lighthouses scattered along an enormous, foggy coastline, each one only lit for a brief stretch of time before going dark again. Some lighthouses might happen to be lit at the same moment as a neighbor close enough to see their light through the fog, but most of them, statistically, will finish their entire burning stretch alone, their light never crossing paths with another lighthouse's brief window of activity, no matter how bright either one happened to shine. What made Forgan's results even stranger is what happened as more time passed within the simulation. As the galaxy aged and more civilizations rose and fell, the total number ever able to establish contact did increase. But even then, the civilizations that did manage to connect tended to form small, isolated clusters rather than one single galaxy-spanning network. Groups on opposite sides of the simulated galaxy sometimes never overlapped at all, running their own separate conversations without ever learning the other group existed. This computer model does not prove that contact is impossible. It suggests something more specific and more unsettling. Even in a galaxy where civilizations are common, the odds of any particular pair actually meeting, exchanging real information, and both benefiting from the conversation before one side disappears, remain stacked heavily against success, simply because of how narrow the overlapping windows of time and space tend to be. Forgan's work has since inspired other researchers to build their own versions of the same model, tweaking assumptions about how long civilizations typically last or how densely they are scattered through the habitable zone. The specific numbers shift depending on the assumptions used, but the overall shape of the result rarely changes. Contact tends to be the exception, not the rule, in almost every version of the simulation tried so far. Everything covered so far has treated time as if it moves the same way for everyone, everywhere in the galaxy. It does not. Albert Einstein proved over a century ago that time itself can stretch and slow depending on gravity and speed, an effect called time dilation, and nowhere in the galaxy is that effect more extreme than near a black hole. At the center of the Milky Way sits a supermassive black hole called Sagittarius, a star, with a mass millions of times greater than our Sun. The gravity surrounding a black hole this massive is so intense that it actually bends the fabric of space and time around it. Get close enough, and something strange happens. Time itself begins to slow down compared to someone watching from farther away, a fact that still sounds more like a plot from a movie than a real, measured property of the universe. This is not science fiction. It has been tested and confirmed using atomic clocks on Earth, which run at very slightly different speeds depending on their altitude and how fast they are moving. Near something as massive as a black hole, that effect becomes dramatic instead of barely noticeable. A civilization capable of building a stable orbit near the edge of a black hole, close enough to survive but still within the extreme pull of its gravity, could experience time passing far slower than it does for the rest of the galaxy. Scientists have even flown atomic clocks on airplanes to measure this effect directly, watching them fall microscopically out of sync with identical clocks left on the ground. Recent research studying orbits near supermassive black holes has found something remarkable. A civilization living in a biologically survivable orbit near a black hole like Sagittarius, a star could experience decades of their own lifetime, while thousands, or even tens of thousands, of years pass everywhere else in the galaxy. From their perspective, only a normal human lifetime would go by. From the perspective of everyone else, entire empires could rise and fall in the meantime. Picture a runner on a treadmill set to an impossibly slow speed, while the rest of the world outside the gym rushes past at normal speed through the window. To the runner, everything feels completely normal. Steps happen one after another, just like always. But when they finally step off the treadmill and look outside, decades might have passed in what felt to them like a single afternoon. This changes the entire conversation about how a truly advanced civilization might choose to survive across cosmic time. Instead of racing to explore the whole galaxy the traditional way, spreading outward planet by planet, a civilization could instead choose to slow its own clock down, using gravity itself as a kind of time machine that lets it experience only a small slice of an almost unimaginably long future. None of this requires physics beyond what Einstein already described more than a century ago. It does not need faster than light travel or any exotic technology science fiction usually reaches for. It only requires enough engineering skill to survive in an extreme environment, close enough to a black hole to bend time meaningfully, but far enough away to avoid being torn apart by its gravity. Take the idea of slowing down time near a black hole and stretch it out to its most extreme possible use. Recent research on this exact scenario has found something almost unbelievable. A civilization capable of building stable, biologically survivable orbits near the edge of a supermassive black hole could achieve a time dilation factor of around 10,000. That means for every single year that passes for that civilization, roughly 10,000 years would pass everywhere else in the galaxy, a ratio so extreme it is difficult for the human mind to picture clearly. At that scale, something extraordinary becomes possible. A civilization living inside that stretched, slowed down bubble of time could send ships out across the galaxy, wait, and receive updates back from those ships, all while experiencing only a human lifetime themselves. Meanwhile, outside their bubble, tens of thousands of years would pass. Entire other civilizations could rise, build cities, and go extinct in the time it takes the black hole dwellers to finish a single generation. This flips one of the earlier problems in this story completely on its head. Remember the challenge of sending a message across the galaxy and waiting tens of thousands of years for a reply, a wait so long it could outlast an entire civilization. A civilization using this kind of extreme time dilation would not have that problem at all. From their point of view, waiting 50,000 years for a reply would only feel like a handful of years, since their own personal clock is ticking so much slower than everyone else's. Picture two friends, one who ages normally, and one who somehow only ages one day for every 10,000 days that pass in the outside world. The friend near the black hole could send a message, casually go about their day, and receive a reply that took 10,000 years to arrive, all while barely noticing much time had passed for them personally. Meanwhile, the friend living at a normal pace would need to wait through the entire 10,000 years themselves, watching their own civilization change dramatically in the process. This is one possible answer to why an advanced civilization might seem to disappear entirely. They may not have gone extinct. They may have deliberately chosen to slow their own experience of time down to nearly nothing, tucked away near the edge of a black hole, waiting out the vast stretches of time needed for a truly galaxy-spanning civilization to take shape, all while barely aging themselves. If a civilization like this exists, hidden in a bubble of slowed time near the galactic center, they would be almost impossible for a fast-moving, normally aging species like humans to ever notice, let alone actually meet, no matter how loudly either side happened to be broadcasting into the dark. This possibility adds an eerie new dimension to the search for extraterrestrial intelligence. Every survey scanning the sky for signals assumes those signals will look roughly the way human technology would produce them, arriving at speeds and frequencies shaped by ordinary time. A civilization living inside a bubble of extreme time dilation would break that assumption entirely, making their presence detectable in theory, but almost unrecognizable in practice. Time dilation near a black hole sounds like a clever survival strategy at first, a way for a civilization to stretch out its own existence across almost unimaginable stretches of cosmic time. But the exact same effect that helps a civilization survive also makes it dramatically harder for anyone else to ever find them, including us. Think back to the friend on the extremely slow clock, aging one day for every 10,000 days outside. From their point of view, everything about their own life feels completely ordinary. But from the outside, watching them would look strange in an entirely different way. Any signal they send out would arrive stretched and slowed down too, its frequency shifted dramatically lower by the same gravity that is warping their sense of time. A message meant to sound like a fast, clear broadcast could arrive somewhere else, sounding more like a long, drawn-out hum, easy to mistake for background noise instead of an actual signal. Researchers studying this effect have found exactly that. Signals sent from an orbit near a black hole would experience something called a redshift, meaning their frequency gets stretched out the farther they travel away from that intense gravity. A radio message that started out sharp and structured could arrive somewhere else, looking like nothing more than a faint, meaningless smear across the radio spectrum, easily filtered out by scientists searching for something that looks more obviously artificial. This creates an uncomfortable possibility. A civilization using time dilation to survive across cosmic ages might be broadcasting constantly, technically speaking, and still remain completely invisible to anyone listening from far away, simply because their signal no longer looks anything like the kind of clear, structured, pattern search programs are trained to recognize. It would be like shouting into a canyon, only to have your voice stretched and distorted so badly by the time it echoes back that nobody recognizes it as a voice at all, let alone a greeting meant for them. This adds an entirely new layer to the silence humanity has been hearing from space. It is not just that other civilizations might be too far away, or existing at the wrong moment in time. Some of them, if they exist at all, might be using the exact same physics that keeps them alive to accidentally erase any trace of themselves from view. If a truly advanced civilization ever does choose to slow its own clock down near a black hole in order to survive across trillions of years, they may end up more hidden than any civilization that simply stayed quiet on purpose, disappearing not through secrecy, but through the strange side effects of bending time itself to survive. This means the search for alien intelligence may need an entirely different kind of instrument than the ones currently in use. Instead of scanning for sharp, structured radio pulses, researchers might eventually need to search for faint, stretched-out smears of energy near black holes throughout the galaxy, signals so distorted by gravity that recognizing them as artificial at all would require rethinking what a message from another civilization is even supposed to look like. Step back from black holes and time dilation for a moment and consider a different, darker explanation for the silence, one that has haunted scientists for decades. It is called the Great Filter, and it suggests that somewhere along the long road from simple, lifeless chemistry to a galaxy-spanning civilization, there exists at least one step that is nearly impossible to survive. The idea works like this. Life has to pass through a long sequence of stages before it can become something capable of building spacecraft and sending signals into space. It has to spark into existence from non-living chemistry. It has to develop the ability to reproduce and pass on genetic information. It has to grow more complex, developing specialized structures and eventually organs. It has to evolve intelligence. And finally, that intelligence has to survive long enough and wisely enough to avoid destroying itself before spreading beyond its home planet. Economist Robin Hanson, who helped popularize the idea, pointed out something unsettling about the math involved. If the odds of passing through every single one of these stages successfully were reasonably high at each step, the galaxy should already be full of visible civilizations. Since it clearly is not, that means somewhere along this chain of stages, there has to be at least one step so difficult, so unlikely, that almost nothing that starts down this path ever makes it through. The unsettling part is that nobody knows exactly where that filter sits. It could be behind humanity already, meaning we already survived the near impossible step and simply have not realized how lucky we are. Or it could still be somewhere ahead of us, waiting, meaning every civilization that reaches our current level of technology eventually runs headfirst into a wall that ends up destroying them before they can spread across the stars. Both possibilities fit the same silent sky equally well, which is exactly what makes the question so difficult to settle. Think of the entire journey from lifeless chemistry to a spacefaring civilization as an obstacle course with dozens of hurdles lined up one after another. If nearly everyone who runs the course successfully gets through most of the hurdles but consistently trips and falls at one particular point, from a distance, it would look like almost nobody ever finishes the race at all, even if the earlier hurdles were relatively easy to clear. This idea reframes the entire silence coming from space one more time. It is no longer just a question of timing, or distance, or physics bending time itself near black holes. It becomes a question of whether there is some invisible wall built into the very process of becoming a civilization capable of reaching the stars. A wall that almost nothing manages to get past. The most unsettling part of the Great Filter idea is that it offers no easy way to check which version is true from the outside. A galaxy with a filter already behind it, and a galaxy with a filter still ahead, would both look exactly the same from Earth right now, silent, empty, and offering no obvious clues about which explanation actually applies to our own situation. Here is the more hopeful version of the Great Filter, one that a growing number of scientists find genuinely convincing. What if the nearly impossible step already happened, billions of years ago, long before humans existed, and humanity is simply one of the rare success stories that made it through without even realizing how close the odds were stacked against survival? The strongest candidate for this early filter is the very origin of life itself. Scientists still do not fully understand how non-living chemistry first organized itself into something capable of reproducing and evolving. Despite decades of research, nobody has managed to recreate that exact transition in a laboratory. It may be an incredibly common, easy step that happens naturally almost anywhere with the right ingredients. Or it may be an astronomically rare fluke, something that has only happened once in the entire observable universe, right here on Earth, purely by chance. If the origin of life truly is that rare, then the silence in space makes perfect sense. Most planets, even ones with the right temperature, the right chemistry, and billions of years of stable conditions, may simply never cross that first threshold at all. They stay lifeless forever, not because anything destroyed them, but because the specific chemical accident needed to spark life into existence never happened to occur, leaving nothing behind but sterile rock and empty ocean under an otherwise perfect sky. Picture buying a lottery ticket every single day for 4.5 billion years, and only winning once. If that win already happened in Earth's deep past, then everything that came after, every fish, every dinosaur, every human being who ever lived, is really just the aftermath of one incredibly lucky roll of the dice that most other planets in the galaxy may simply never get. There is a second strong candidate for an already survived filter: the jump from simple bacteria to complex cells with internal structures, called eukaryotes. On Earth, this transition took roughly 2 billion years after life first appeared, and as far as scientists can tell, it may have only happened successfully one single time in Earth's entire history. With every complex organism alive today descending from that one lucky event, that single event set the stage for everything that eventually followed, from the first jellyfish to the first human. If either of these steps, the origin of life or the jump to complex cells, represents the true great filter, then humanity may already be standing safely on the other side of the hardest part of the entire journey. Everything that comes next, building technology, surviving as a species, and reaching out into the galaxy, would be difficult, but not nearly as astronomically unlikely as the step already left behind us. Some scientists find this version of the story genuinely comforting. It suggests the danger humanity faces going forward, while real, may not be nearly as steep as the danger already survived without anyone alive today ever realizing how close the odds were stacked against it. The hardest part of the climb, under this version of events, is already behind us, buried deep in Earth's ancient rock record. The jump from simple bacteria to complex cells deserves a closer look because the timeline involved is almost impossible to fully picture. For roughly 2 billion years, Earth's oceans were filled with nothing but simple, single-celled organisms. No plants, no fungi, no animals, just bacteria and similarly basic microorganisms, floating and multiplying, generation after generation, without any of them evolving into anything more complicated. 2 billion years is longer than the age of most rocky planets that have ever formed anywhere. It is nearly half the current age of the entire universe. For all that time, Earth's biosphere remained essentially stuck at the same basic level of complexity, cycling through countless generations of simple cells without producing a single organism with a nucleus, let alone anything resembling a plant or an animal, an astonishingly long stretch of nothing changing at all. Then, at some point roughly 2 billion years ago, something remarkable happened. Scientists believe one simple cell somehow absorbed another simple cell, and instead of digesting it the normal way, the two merged into a single, more complex organism. That absorbed cell eventually became what scientists now call a mitochondrion, a tiny internal structure that generates energy and exists inside nearly every complex cell on Earth today, including every cell in the human body. This single merger appears to have happened only once in Earth's entire multi-billion-year history. Every plant, animal, fungus, and complex organism alive today all descend from that one original successful merger. It never happened again independently, as far as scientists can tell, despite 2 billion more years passing since then, filled with countless trillions of simple cells that never managed to repeat the same trick. Picture a lock that has only ever been picked successfully one single time, despite millions of attempts made against it every single day for 2 billion years straight. That is roughly how rare this transition appears to have been. It was not guaranteed. It was not something evolution was steadily building toward the whole time. It may have simply been an extraordinarily unlikely accident that happened to work exactly once, in one cell, in one ocean, on one small planet. If this transition, from simple cells to complex ones, represents a major piece of the Great Filter, it would explain a great deal about the silence coming from space. A planet could easily be covered in simple, thriving life for billions of years. Exactly the kind of life NASA has been searching for on Mars and other worlds, without ever taking the next step toward anything complex enough to eventually build a telescope and wonder if anyone else is out there. This possibility carries a strange kind of weight when you consider how many worlds might be quietly covered in nothing but pond scum, thriving and stable, generation after generation, for billions of years, without any of it ever amounting to more than that. From orbit, such a planet might show clear signs of biology, oxygen in its atmosphere, chemical fingerprints of living processes, and still never produce a single mind capable of noticing another world doing the exact same thing. Not every scientist believes humanity has already survived the hardest part of the journey. A darker version of the Great Filter suggests the nearly impossible step is not behind us at all. It is still ahead, waiting for every civilization that reaches roughly humanity's current level of technology, and almost none of them ever manage to get past it. Under this version of the idea, the origin of life might be relatively common throughout the galaxy. The jump to complex cells might not be as rare as it looks from Earth's single example. Intelligence might evolve fairly often, given enough time. But somewhere just beyond where humanity currently stands, right around the point where a species develops powerful technology, something almost always goes catastrophically wrong. Philosopher Nick Bostrom described this exact fear when he first popularized the modern version of the Great Filter idea. He pointed out that a filter is only truly terrifying if two things are both true. Almost every civilization that reaches a certain level of technology eventually discovers whatever the dangerous threshold is, and discovering it almost always leads to disaster, whether through war, environmental collapse, or some other kind of self-inflicted catastrophe that ends the civilization before it can spread beyond its home planet, no matter how promising things looked just before the fall. This version of the filter would explain the silence in a much more unsettling way. It would mean the galaxy is not empty because life is rare. It would mean the galaxy is empty because civilizations keep getting close, again and again, only to destroy themselves right around the same stage humanity currently finds itself in, the stage where technology becomes powerful enough to reshape an entire planet, for better or for worse, in a shockingly short span of time. Picture climbing a mountain where nearly every previous climber successfully made it most of the way up, only to fall from the exact same ledge near the summit, over and over, for reasons nobody who reached that ledge ever survived to explain. From a distance, all you would see is a mountain covered in climbers who never reached the top, with no clear evidence of what specifically went wrong at that final stretch. If this darker version of the Great Filter is correct, It means humanity's current moment in history matters more than almost any other point in the story so far. Every civilization capable of building rockets and world-altering technology may be standing at the exact same dangerous ledge right now, with no guarantee that the climb from here forward ends any differently than it apparently has for everyone who came before. This version of events does not necessarily mean doom is guaranteed. It means the outcome remains genuinely undecided, shaped by choices still being made today, rather than locked in by anything that happened billions of years in the past. Unlike the origin of life, or the jump to complex cells, this potential filter is not buried in ancient rock. It is playing out in real time, in decisions humanity is making right now about technology, cooperation, and survival. Every idea covered so far, the timing of stars, the size of the galactic habitable zone, gamma-ray bursts, causal contact, time dilation, and the great filter, shares one thing in common. Each one adds another layer of difficulty on top of the last, and every layer stretches across enormous amounts of cosmic time. The longer you look at this problem, the more ways there turn out to be for two civilizations to simply miss each other. Think about all these filters stacked together like a tower of transparent glass sheets, each one covered in random splatters of paint. A single sheet might not block very much light on its own, but stack 10, 20, or 30 of these sheets together, each one adding its own random pattern of coverage, and eventually almost no light manages to pass all the way through every single layer at once. That is roughly what happens when you combine the timing problem with the distance problem, the survival problem, and the detection problem, all stacked on top of each other across billions of years. A civilization needs the right kind of star, one that lives long enough for complex life to develop. It needs to sit inside the narrow galactic habitable zone, away from both the dangerous chaos near the core and the element-poor emptiness of the outer galaxy. It needs to avoid getting wiped out by a gamma-ray burst or some other catastrophic event during the billions of years complexity takes to develop. It needs to survive whatever the great filter turns out to be, whether that filter sits behind it or still lies ahead. And even after clearing every one of those hurdles, it still needs to exist during a narrow window of time that happens to overlap closely enough with another civilization for a real, causal conversation to become possible. Every additional zero added to any one of these timescales, whether it is the trillions of years a red dwarf can burn or the tens of thousands of years a single message takes to cross the galaxy, multiplies the number of ways two civilizations can end up separated, even if both of them technically exist somewhere in the same galaxy at some point in its long history. This is why the silence coming from space does not need a single dramatic explanation, like an alien invasion or a hidden government cover-up. It might simply be the natural result of stacking enough independent obstacles on top of each other, each one reasonable on its own, but devastating when combined across a timescale as enormous as the one the universe actually operates on. Even so, none of this rules out the possibility that somewhere, right now, another civilization is looking up at its own sky, wondering the exact same thing humanity is wondering, separated from us, not by anything dramatic, but simply by an unlucky arrangement of timing across an almost incomprehensibly large stretch of cosmic history. That thought deserves to sit for a moment. It means the loneliness humanity feels when looking up at a silent sky may not be a permanent, built-in feature of reality. It may simply be a temporary condition, one shaped entirely by an accident of timing that could, given enough patience and enough luck, eventually resolve itself into something very different. Even a civilization that clears every filter covered so far, one that develops on the right kind of star, sits safely inside the galactic habitable zone, and somehow survives the great filter, is not guaranteed a long life afterward. The universe is filled with sudden, unpredictable ways to end a civilization's story early, long before it ever gets the chance to reach out and find anyone else. A nearby supernova is one of the most dramatic examples, When a massive star finally runs out of fuel, it can explode with enough force to send dangerous radiation and high-speed particles racing outward in every direction. A supernova occurring within roughly 50 light-years of an inhabited planet could strip away that planet's protective ozone layer, exposing the surface to lethal levels of radiation from its own sun. 50 light-years sounds impossibly far by human standards, but on a galactic scale, it is close enough that scientists consider it a real, credible threat. A rogue black hole presents an even stranger danger. Not every black hole sits quietly at the center of a galaxy. Some can be flung out of their original systems by violent gravitational interactions, sent drifting silently through interstellar space with no light of their own to give away their location. A black hole like this could pass uncomfortably close to a solar system without any warning at all, its gravity subtly disturbing the orbits of planets and potentially sending smaller objects, like asteroids, on a collision course toward an inhabited world. Even without anything as dramatic as an explosion or an invisible black hole, a much slower and quieter threat can end a civilization's chances just as effectively. Climate shifts, whether caused naturally by a planet's own star growing brighter with age, or caused by a civilization's own technology altering its atmosphere, can slowly transform a once thriving world into some place no longer capable of supporting complex life. This kind of ending does not require any single dramatic event. It only requires enough time and enough gradual change to eventually cross a threshold that cannot be undone. Picture a candle burning steadily in a closed room. For a long time, nothing seems to change. The flame stays the same size. The room looks the same, but the oxygen is slowly running out the entire time, invisible and unnoticed, until the moment finally arrives when the flame simply cannot stay lit any longer, snuffed out not by any single dramatic event, but by a slow, steady process that had been quietly working the entire time. Any one of these threats, sudden or slow, could end a promising civilization's story long before it ever reaches the stage of sending a signal into space, adding yet another layer of uncertainty on top of everything already working against two civilizations ever finding each other. None of these dangers require malice or intent. A supernova does not choose its target. A rogue black hole does not aim itself at a specific world. A slowly warming climate does not decide to punish a species for its mistakes. These are simply the ordinary, indifferent hazards of existing inside a universe that was never designed with any particular planet's safety in mind. Hazards that every civilization, anywhere, would eventually have to face. Bring every idea covered so far back together, and something becomes clear. The Fermi paradox does not get easier to solve the more carefully you study it. It gets worse. Every layer added to the problem, whether it is the staggered birth of stars, the narrow habitable zone, the near impossible steps in the Great Filter, or the way gravity itself can stretch and warp time near a black hole, adds another way for two potential civilizations to miss each other entirely. Most explanations people first imagine for the Fermi paradox focus on space. They imagine two civilizations, both alive right now, simply too far apart to reach each other. That version of the problem is difficult, but at least it feels solvable. Build faster spacecraft. Build more powerful telescopes. Eventually, distance might be overcome through better technology. Time is a completely different kind of obstacle. You cannot build a faster spacecraft to reach backward into a civilization that already went extinct millions of years ago. You cannot build a more powerful telescope to see forward into a civilization that will not exist for another billion years. Space can be crossed, slowly, given enough patience and technology. Time only moves in one direction, and it moves at different speeds depending on where you happen to be standing in the universe. As the black hole example proved, a fact that makes it far stranger than any ordinary obstacle humans have ever tried to overcome before. This is why adding time into the equation makes the paradox so much stranger than the simple version most people are familiar with. It is not just a question of whether intelligent life exists somewhere in an enormous but ultimately fixed galaxy. It is a question of whether that life exists during the same narrow slice of an ever-expanding, ever-aging timeline, one that stretches across billions of years already, with trillions more still to come. Picture two people trying to find each other inside a building with an infinite number of floors, except one of them is only allowed to search for a single minute before the entire building resets and rearranges itself. Even if both people are searching as hard as they possibly can, the odds of them ever standing on the same floor, at the same moment, before everything resets again, shrink dramatically the larger and stranger the building becomes. The galaxy is that building. Civilizations are the searchers. And the resets, the endings, the extinctions, the trillions of years still left to unfold, keep happening over and over, making the odds of any two minds actually meeting look less like a guarantee and more like an extraordinary stroke of luck that would have to happen against nearly impossible odds. This is the true weight of adding time into the Fermi paradox. Distance, at least, holds still long enough to be measured, mapped, and someday crossed. Time keeps moving, keeps resetting, keeps rearranging the entire puzzle every time a star dies or a new one ignites, making the search for another mind out there feel less like exploring a map and more like chasing a shadow that never stops shifting. After everything covered so far, the silence coming from space can feel discouraging. Filter after filter, obstacle after obstacle, each one stacking on top of the last. But there is a genuinely hopeful thread running through all of this, one worth returning to directly. The universe is not running out of time. It is barely getting started. Remember the stelliferous period, the long stretch of cosmic history, when stars provide enough energy to support planets and potentially life. That period is expected to last for trillions of years, and the universe so far has only existed for a tiny fraction of that total span, less than 1% by some estimates. If humanity manages to survive, even for what feels like a long time by human standards, a few thousand more years, a few 100,000 more years, that would still represent an almost immeasurably small sliver of the time the universe has left to offer. This means humanity is not staring down a closing window. It is standing at the very beginning of one of the longest windows imaginable. Every challenge covered in this story, surviving the Great Filter, avoiding a nearby supernova, developing technology responsibly enough to avoid self-destruction, becomes less like an impossible final exam and more like an early test, one attempt among what could eventually be countless future attempts made by countless future civilizations across the trillions of years still ahead, each one learning a little more than the last. Picture standing at the edge of an ocean so vast that the far shore cannot even be imagined, holding nothing but a single small boat. The size of that ocean might feel overwhelming, even frightening, but it also means there is no need to have already crossed it by now. There is no deadline that has already quietly passed without anyone noticing. The entire journey, for humanity and for whoever else might be out there, is still almost entirely ahead, with far more of the map left unexplored than already charted. Every idea explored throughout this story, from Fermi's napkin math to gamma-ray bursts to black holes bending time itself, points toward the same underlying truth. The Fermi paradox does not exist because the universe failed to produce life. It exists because the universe is still in the process of producing it, slowly, unevenly, across a length of time so enormous that 13.8 billion years barely counts as a beginning. If the universe truly does have trillions of years left to run, then the silence humanity hears today is not a verdict. It is simply where the story currently stands, on a timeline so long that almost everything interesting still has not happened yet. That reframing matters more than it might first seem. A verdict implies the case is closed, that the outcome has already been decided and nothing left to do but accept it. A timeline still unfolding implies the opposite, that the most important chapters have not been written and that humanity still has a meaningful role to play in deciding how the rest of the story goes. Flip the entire question one final time. Instead of asking whether humanity will ever hear from another civilization, ask a different question. What if, someday, far in the future, humanity becomes the civilization that someone else is desperately hoping to hear from? Everything covered throughout this story suggests that being early is not a small detail. It might be one of the most important facts about humanity's entire existence. If most of the galaxy's longest-lived stars are red dwarfs that have barely reached the age needed to support complex life, and if the universe still has trillions of years left in its stelliferous period, then civilizations capable of reaching out into the stars may become dramatically more common as time goes on, not less. Humanity, if it survives, could end up remembered not as a rare exception, but as one of the first examples of something that eventually becomes common throughout the galaxy. Think about the very first city ever built in human history. At the time, nobody living there could have imagined the millions of cities that would eventually follow, spread across every continent on Earth. That first city was not the peak of what cities would become. It was the starting point, an early example of something that would go on to define nearly every part of how humans eventually chose to live. The builders of that first city were, in a very real sense, ahead of their time, without any way of knowing just how far the idea would eventually spread. Humanity might be standing in a similar position on a much larger scale, an early technological civilization in a galaxy that has barely had enough time to produce very many others. If that is true, then everything humanity does over the coming centuries, every signal ever sent, every message ever recorded, every piece of technology ever built and refined, could end up mattering to civilizations that will not even exist for millions or billions of years to come. A message sent today, wandering through the galaxy for tens of thousands of years, might not find its intended audience among any civilization currently alive. It might instead be discovered by a civilization that has not been born yet, one still waiting patiently on a red dwarf world for its own 4 billion-year climb toward complexity to finish, thousands or millions of years from now, long after every trace of the people who first sent that message has faded from memory. If humanity manages to survive long enough, choosing wisdom over self-destruction at exactly the ledge where so many other civilizations might have fallen, it would not just mean humanity avoided its own ending. It would mean humanity became one of the very first voices in a conversation that could stretch across the rest of the universe's existence. A voice some future civilization might eventually be straining to hear. That possibility places an enormous, almost uncomfortable weight on this exact moment in history. Every generation before this one lived and died without ever knowing whether humanity would make it far enough to matter on this scale. The generations alive today, and the ones coming soon after, may be the ones who actually decide the answer. Every idea in this story eventually leads back to the same simple, unavoidable fact. Time is the real force behind the Fermi paradox, not distance and not silence. Stars are born on staggered schedules, stretching across billions of years. Complex life needs nearly 4 billion years just to develop. If Earth is any guide, messages take tens of thousands of years to cross the galaxy. Black holes can stretch a single lifetime into 10,000 years for everyone else. And somewhere within all of that, humanity exists for a stretch of time so brief it barely registers against the age of the universe itself. But brief does not mean unimportant. Every year humanity survives is another year added to a signal that is, in a very real sense, already in flight. Every message ever sent from Earth, every deliberate broadcast aimed at a distant star, every accidental radio signal that leaked out into space over the past century is still traveling right now, carrying a small piece of this exact moment in history outward into a universe that has trillions of years left to receive it. A universe that has barely finished reading the opening line of what could become an extraordinarily long story. Humanity did not arrive late to an ancient, crowded galaxy already full of established civilizations. The evidence throughout this story points towards something closer to the opposite. Humanity may have arrived remarkably early, standing near the very beginning of the stelliferous period, at a moment when very few, if any, Other civilizations have had the time needed to reach the same point. That changes what the silence actually means. It is not proof that humanity is alone forever. It is not proof that every civilization eventually destroys itself. It is simply what an early moment sounds like in a universe still working through the slow, staggered process of producing minds capable of asking these exact questions in the first place. Every second that passes from here forward is a second where humanity has the chance to keep building, keep surviving, and keep adding to a story that may only be in its opening pages. The signals already sent will keep traveling regardless of what happens next. But whether there is anyone left to send the next one, and the one after that, depends entirely on choices still being made today. Choices about whether humanity survives long enough to become the very civilization that some future world, thousands or millions of years from now, finds itself desperately hoping to hear from. The silence overhead tonight is not an ending. It might simply be the sound of a universe that is only just getting started, with humanity standing near the front of the line, holding a message that time itself has not finished delivering yet. Fermi asked his question over lunch nearly 80 years ago, never imagining how far the answer would eventually stretch, across billions of years already gone and trillions still to come. The napkin is long lost. The question outlived it, and may end up outliving every generation that ever tries to answer it, passed down the way a torch gets passed down a long, unfinished relay race across the stars.